In this video, I'll talk about a very important relationship between current density, resistivity, conductivity, and from those relations, we'll derive an equation that we are very familiar of, that is called Ohm's law. Okay, and in a separate video I will talk about what is the resistivity, conductivity, and the resistance. So here the goal of this video is to introduce the relationship between all these physical quantities: the current density, resistivity, and conductivity. We already have talked about the current density. The current density is defined as a current per unit cross-sectional area. So this is the current flowing through a conductor, and I is the cross-sectional area. And we already have derived this equation. So this is NQVD, and this VD is the drift velocity, N is the charge carrier density, and Q is the charge of each charge carrier. So if we have, let's say, a conductor, and if we increase the electric field, how can we increase the electric field? There are different ways of increasing this electric field. The one way is just by you applying more potential difference, or by shortening or by reducing the length of the conductor. Either way, you can increase the electric field. The current density in a conductor is directly proportional to the electric field. So the current density is directly proportional to electric field. So the relationship between the current density, electric field, is given by this equation here. And there is a constant, this constant here. This constant, sigma, this is pronounced as sigma. The symbol is called sigma, and this symbol, or this sigma here, represents the electrical conductivity. So this quantity is the electrical conductivity. The electrical conductivity of a material measures the ability of a material to conduct electric current. The greater the value of sigma is, the greater the value of sigma is, the higher the current will be flowing through the conductor, or the more current will be flowing through the conductor, or it has the more ability to conduct electric current. And this is the material's property. The sigma, or the conductivity is the material property. What does it mean? This means it does not depend upon the length of the conductor. It doesn't depend how does it look like. It could be in any form. It could be cylindrical form, it could be any arbitrary form, it could be cubical form. The conductivity does not depend upon the shape, it does not depend upon the length, it doesn't depend upon the size, it only depends upon the material. Okay, so for example, the conductivity has one value for one particular material. Let's say for copper, if we go to another material, let's say brass, it will have another value. So this conductivity, this sigma, distinguishes the electric current ability, the ability of a material to conduct electricity. Okay, so if you have to choose a material that can conduct better electricity, the parameter that you have to look is the sigma here. And here I'm just talking only about the DC, the direct current, which is not fluctuating with respect to time. Of course, this sigma might change, or it does in fact change with the AC current. So that's a separate topic here. So if you have so if you have to choose a material that can better conduct electricity, the parameter that you will look is the sigma here. Okay. So now let's say you have a conductor here, this conductor, which has a uniform cross section, and we apply a battery, that's a potential difference delta V, and the length of the conductor is L. As we apply the potential difference, then it sets off an electric field in the conductor, and this electric field value is given by this quantity here, delta V over L, which is the potential difference divided by the length. Now let's plug in all the values here. Let's plug in this value into this equation. So J, we have this J here, sigma as it is, and instead of A, instead of this E, instead of this electric field, I'm just plugging this value here, delta V over L. And we know that this J is also current per unit area. So I'm simply writing J as a current per unit cross-sectional area, sigma delta V over L as it is. And I'm solving here for delta V. The delta V is now, in fact, this L will come this side, L over sigma A times I. If so we have L, sigma, and A. I'm just putting them together. And this is I, the current. What does this shows you? The potential difference or the current in a circuit is directly proportional to the applied potential difference. And we have called this term, all the terms within this bracket is called the resistance of the material. Okay, this R here we have just described here, R, which is L over sigma over A, is called the resistance of the conductor, and the unit of this resistance is ohm. So we have defined this one as the physical quantity, that is the resistance or electrical resistance. This quantity in fact measures how strongly the material opposes to the flow of charge carriers. Okay, so this quantity, the electrical resistance, is the materials, or is this quantity tells you how strongly the material is going to oppose the flow of the charge carriers, or in case of metals, to the flow of electrons. And this quantity depends upon the length, that's what it shows here. So the greater the length is, the more oppose it will do to the flow of the electrons, and it is inversely proportional to the cross-sectional area. That means if you have a larger cross-sectional area, then the electrons can easily flow to the conductor. So what does that mean? That means, let's say you have the two conductors here, one with a smaller cross-section area and the other with a bigger, the same length. Here I'm talking about the same length here, but this one has more cross-section area. And if these two have the same length, that means this one will have a smaller resistance, or this one will oppose electrons of significantly smaller. And you can think about this one, the electrons has now more area, so it can flow easily compared to this one. Okay, and I'll talk about all these variations in a separate video here. My goal here is to introduce with the parameters. So this relation, in fact, that we're familiar with is called the Ohm's law. And but technically this is to be called the Ohm's law. Okay, this has to be called the Ohm's law. J equals to sigma E is in fact true Ohm's law. This equation is simply a derivation, just another equation that is coming from this equation. Okay, so far We talked about the Ohm's law. We have this equation is called Ohm's law, and this quantity is called the resistance, and the unit is ohm. Now let's talk about another term here, the resistivity. The resistivity is denoted by this term, which is pronounced as rho, RHO. This is pronounced as RHO. And this is nothing but a reciprocal of conductivity. So we have defined conductivity sigma. All right, here you see this sigma here. So the resistivity is just the reciprocal of conductivity. That means if a conductor is much efficient in conducting electricity, which also means it opposes very small, it does have very small opposition to the flow of the charge carriers. Okay, so a conductivity is just a reciprocal of resistivity, or resistivity is just a reciprocal of conductivity. So electrical resistivity, the measures materials ability to oppose the flow of electric current or to the flow of charge carriers. And the unit is ohms. This is pronounced as ohm times the meter. All right, that's the unit of the resistivity. So here are a few important points that I have made here. The current in any conductor happens because of the potential difference. Okay, the current, the electrical current in any electrical circuit or any conductor happens because of the applied potential difference. Or in other words, we can say the potential difference is the source of the current. Without potential difference, if you have a conductor, if you have this conductor, let's say here, and if these two are at the same potential, then there will be no current. But if there exists a potential difference, then there must be current into it. So the current is the outcome of the potential difference, or the potential difference is the source of the current. Okay, and the resistivity, conductivity does not change with the cross-sectional area. As I mentioned before, the resistivity and the conductivity is the material's property. It doesn't matter how does your material looks like. It might be looking this way, it might look like a perfect cylinder, or it might look like some haphazard or more weird shape. Resistivity does not change, conductivity does not change. What changes is the resistance. Okay, the resistance does depend upon the length, it does depend upon the shape, it does depend upon the geometry of the material. So as an example here, I have chosen the four simplest possible the conductors here with the different lengths and the different cross-sectional area. So this one has a, let's say, called length L, and the cross-sectional area is A. And in this figure, I have increased the length by 2 times. So if this is 5 meter, it will be 10 meter, but the cross-sectional area is exactly the same. So now you have to tell me which one will have higher resistance. So you remember this equation here.